Hello APC Mechanics students, today we will solve the past paper FRQ 2013 exercise 2. Then let me start. A box of mass m initially at rest, this is important to indicate that the initial speed is 0, is acted upon by a constant applied force of magnitude Fa as shown in the figure above. The friction between the box and the horizontal surface can be assumed to be negligible, but the box is subject to a drag force of magnitude kV, where V is the speed of the box and K is a positive constant. Express all of your answers in terms of the given quantities and the fundamental constant as appropriate. Fundamental constants refer to, for example, at least the pull of gravity. The givens are given by K and the mass m basically. Now V is considered as a variable, not a constant, and we have the magnitude of the applied force Fa. Alright. Then the dot below represents the box. Draw and label the forces, not components, that act on the box. They didn't give us much instructions about how to draw the FBD. That's fine, because we know that the forces must be represented by distinct arrows starting on the point and pointing away. Then because the box have a mass, it will be subjected to the pull of gravity, which is down, and it will be balanced by the normal push. So I will try to draw the normal push equal in magnitude to the pull of gravity. That's the pull of gravity, and that would be the normal push. We have the pushing force, the applied force of magnitude Fa, which is considered horizontally to the right. And we have the drag force. Now here in this case we can consider three different states. At the beginning the box started from rest, which means that the drag force would be 0. At the final stage, reaching the steady state, the drag force will be balanced by the force Fa, and they will be equal in magnitude. If they didn't specify which state are we will take the more general state, consider the transient state in which the drag force would be less than the applied force. That would be Fd for the drag force. Now write, but do not solve, this is important, a differential equation that could be used to determine the speed v of the box as a function of time t. If you need to draw anything other than what you have shown in part A to assist in your solution, use the space below. Do not add anything to the figure in part A. Remember that always whenever we construct the FBD, we should keep it as it is. We cannot draw any components or any additional stuff on the FBD. So we're gonna leave it like that. And we know that differential equations are basically applied from big laws like Newton's second law. Then let me say apply a Newton's second law. And the law is given by F naught equals ma. And remember that it is important to mention this law. Usually they give it a certain mark, like 1 mark or half a mark, based on the marking scheme. Now we need to list all the forces at this stage. We need to list all the forces that are acting on the box. We didn't enter yet any projections. Then we have the drag force, or let me start by the pull of gravity, plus the normal push. I would always like to proceed in this order: pull of gravity, normal push, the force Fa, plus the drag force acting to the left, equals to ma. Notice that I have added them vectorially. Each quantity has a vector, and there is no plus or minus sign because we didn't project. And in this case, let me project along the horizontal. Then projection, along the horizontal, and here I will assume that the positive direction is to the right. The pull of gravity has no projection along the horizontal as well as the normal push. Now Fa would be plus Fa, and the drag force which is acting opposite to the motion, that would be minus Fd, and remember that the acceleration has no projection. Now here we're searching for the differential equation. So basically differential equation of what? Of v, which represents the speed, and the speed appear from the drag force, because we know that the drag force is given by k multiplied by v, in which v represents the speed. Now Fa would be kept as Fa minus kv equals to ma. Now considering Fak and m are constants, we have two variables given by v and a, then they can both convert it to each other using calculus, using v or a is dv by dt, which converting this equation into a differential one. And so you can ask yourself if v should be converted to a or a converted to v. Since they're asking about the differential equation of v, so we will convert a to be v. However, if they're asking for the differential equation of a, we would convert v to be a. Now that would be Fa minus kv equals m dv by dt. Now dragging this to the other side, we would have that Fa is m dv by dt plus kv. Now reading the equation from right to left, that would be m dv by dt plus kv equals Fa. And remember that it's always good to write the differential equation into the canonical representation, leaving the derivative with the coefficient equal to 1. So divide everything by m. That would give us a differential equation given by dv by dt plus k over m, the coefficient, multiplied by the variable v, equals to Fa divided by m, and that is our differential equation that we're searching for. And here notice the following: this is an acceleration dv by dt should be equated by an acceleration. Usually it's given by g if it's falling. Here in this case it's moving along a surface, then it would be represented by force over mass, which is acceleration. Now determine the magnitude of the terminal velocity of the box. Now the terminal velocity can be determined by two methods. Either if we have the solution v explicitly as function of time, we take the limit t tends to infinity. However, in this case we didn't solve the differential equation yet, so another way to do that by considering the terminal state. So we can say at the terminal velocity, the forces are balanced. About which forces we're talking? We're talking about the drag force will be balanced by Fa, because it will be moving at a constant velocity, which is the terminal velocity. Fd can be replaced by kv, and this v would carry the subscript t, indicating that it's the terminal velocity, and that would be equal to Fa. And we're searching for the terminal velocity, then the terminal velocity would be given by Fa divided by k. Then what does this speed or velocity represent? That would be the maximum velocity reached by the box submitted to two forces given by Fa, which is a constant force, and the drag force, which is a variable force. Now in part D, they're telling us use the differential equation from part B to derive the equation of the equation for the speed v of the box as a function of time t. Assume that v equals to 0 at time t equals to 0, and this has been stated explicitly in the text that the mass m has started initially from rest. Then let's drag our differential equation that we have determined. Then I will copy this here. We have dv by dt plus k over m v equals to Fa divided by m. And remember that this condition will allow us to determine the expression of the constant c of integration. Now the steps that we will follow are many. For this reason, I will split my page into two. And the method that I'm gonna follow in order to solve this differential equation is known as the separation of variables. Then let me start. We need to separate the two variables that we're gonna integrate over, given by v and t. So as a first step, we will move this member to the right hand side. Then dv by dt equals fa over m minus k over m multiplied by v. Usually the next step is to do the common denominator between these two expressions, and the common denominator would be the inertia, which is the mass. In this case it's already done. Then let's factor 1 over m out. Then that would be fa minus kv. Now if you notice carefully, we can separate the variables v and t. This is, we can suppose that that would be a variable completely dependent on v, and this is a variable completely dependent on t. Then it can be written as dv divided by fa minus kv equals 1 over m multiplied by dt. So what I have done here, I moved this down and I moved this up. So dv by dt on one hand can be understood as an operator. On the other hand, dv can be understood as a number and dt can be understood as a number, so they can be taken up and down easily. Now we're ready to integrate on both sides, making sure that the left member completely depends on v and the right member completely depends on t. And our integral would be an indefinite integral, because later on we will handle the constant of integration c. Now that would be the integral of dv divided by fa minus kv, which is equal to 1 over m. Then remember that if m is constant, then 1 over m is constant. They can be dragged out, and that would be a linear term t plus a constant of integration c. Once we add a constant of integration c to our equality, no need to add it anymore, because a constant plus a constant would be a constant. Anything which is a constant multiplied by a constant would be itself a constant. And now it's left to integrate the left hand side. This integral cannot be found in the table of integration, and it can be managed again using the change of variable. Then let me say let a new variable u equals fa minus kv. Then what I will try to do here to convert this integral from being completely dependent on v to be completely dependent on u. Then the differential form of u would be given by the derivative of this multiplied by v dv. The derivative of fa is a constant would be 0. K is a constant, but it will be safe because it's multiplied by v. Then that would be minus k dv. And in the integral we're searching for dv. Already this has been transformed to u. So that would be dv equals du divided by minus k. Then this integral dv by fa minus kv can be written as the integral of, so this is a v and this is a v. That would be 1 over u, because I have defined this to be u. Now what about dv? dv has been identified by du over minus k based on our change of variable. Then du divided by minus k. Minus 1 over k is a constant, can be dragged out, so this is minus 1 over k, the integral of du over u. And we know that the integral of du over u is ln u, so that would be minus 1 over k ln u. Now minus 1 over k ln u is given by that. And that would be equal to the right hand side of our equality given by 1 over m t plus c. And let me do here a side remark. So what do we expect from the expression of v to be? It would be something like v, a terminal velocity, multiplied by 1 minus e to the power minus something multiplied by time, which is an exponential growth. Now before getting rid of ln, we need to move this factor to the other side. So how we're gonna move it? Suppose here this is divided by minus k. Let me remove this minus sign. So minus k would be multiplied by this and by that. Now minus k multiplied by a constant can be reformulated as a constant itself, and we would have that ln of fa minus kv equals minus k over m t plus a constant c. And now we can get rid of the ln function by considering the exponential of both sides. That would be fa minus kv equals e to the power minus k over m multiplied by t plus c. And let's recall the identity given by e to the power of a plus b equals to ea times eb. Then by that we have e minus k over m t plus c equals e minus k over m t multiplied by e to the power c, and this can be reformulated to be the constant c again. Then that would be fa minus kv equals to c multiplied by e minus k over m t. Basically this is our differential equation, but we're not gonna keep it like that because we need to search for c, and c can be determined using this condition. So replacing t by 0, that would be fa, the initial velocity is 0, equals to c multiplied by e to the power of 0, because that multiplied by 0 would be 0. Then fa equals to c. Now replacing this here, because e to the power 0 is 1, that would be fa minus kv equals fa multiplied by e to the power minus k over m t, and we're searching for the expression of v. This v depends on time. We will take this to the right hand side and this to the left hand side. Fa minus fa e to the power minus k over m multiplied by t equals to kv. Now in this case kv equals to fa, if we factor out fa, that would be 1 minus e minus k over m t, and here we can divide by k. Then the velocity v as function of time is given by the terminal velocity that we have determined previously, given by fa over k, multiplied by 1 minus e minus k over m. This is an m multiplied by t as we expected. Now part E, which is the last part of this exercise. On the axis below, sketch a graph of the speed v of the box as a function of time. Explicitly label any intercepts, asymptote, maxima or minima with numerical values, all algebraic expressions as appropriate. Although they're saying let's plot v represents velocity, but referring for v to be the speed, and we need to be very careful. There is a difference between velocity and speed, and that difference always arises whenever we are moving in the negative direction. Luckily here, because our motion occurs to be in the positive direction as we assumed, so no need to worry about anything. We know that in such type of systems the velocity is an exponential growth reaching an asymptotic value, which is the terminal velocity. Then the terminal velocity is the factor which is here given by fa divided by k, and by that we would have done the asymptote. It starts from an initial value given by 0, so we expect that the function will grow something like that. Now what is important here is that your curve should appear as an exponential function starting from 0 and trying to reach the asymptote after a good amount of time, and the asymptotic value is given by the terminal velocity. Then that's it for me in this video, guys. See you soon in a new one.